If you've ever started tackling a new complex subject, especially math, and felt that immediate overwhelming paralysis of information overload, well, you know the feeling. It's not just that the concepts are hard, it's that you don't even know the structure, the vocabulary, or the map. Our mission today is to dive deep into a unique instructional architecture found in a curriculum called the Math Map. We've got a stack of source material here revealing how this system is explicitly designed to take those difficult, high-level mathematical concepts and transform them into the familiar. It really relies on deep, long-term pattern recognition. It sounds like a shortcut to confidence.
Yeah, and what's fascinating here is that the entire enterprise is rooted deeply in the classical method of learning, grammar, dialectic, and rhetoric. The sources make it clear that the philosophy is key. Math study isn't treated as a subject you just complete, but more like a lifelong process. When you encounter advanced algebra, you're basically operating as a grammarian of a new, unfamiliar language.
A grammarian, okay? And to anchor that lifelong process, this curriculum lays out what they call a 13-year grammar program. The focus is incredibly specific, mastering just 16 fundamental functions, things like power, logarithmic, trigonometric, exponential, and so on. So these 16 functions are the entire vocabulary, the actual building blocks for every single algebraic function a student will ever encounter, whether they stop after high school or, go on to university calculus.
That's the idea. So if the ultimate goal is mastery of these 16 building blocks, the question becomes, how do you keep the learner oriented during the pretty long 13-year journey? Well, the answer seems to lie in these things called the frames. You should think of these not just as pages, but as 4 supplemental tools that physically surround the weekly lesson pages, 3 pages up front, 1 in the back. They exist explicitly to empower the learner, really, to direct their own study and place the daily work into the broadest possible context.
Okay, let's look at the first 2 frames. These seem to focus on context and synthesis. Frame number 1 is simple, but sounds powerful. The Math Map. It's reprinted every single week.
Every week. It's a visual representation of the whole curriculum, showing the student exactly where they are, which domain, which lesson number they're on. It turns math into, well, a journey with landmarks.
Yeah, I can see how that would be a huge boost to morale.
Exactly. It lets the learner glance back at the lessons they've successfully navigated, their accomplishments, and look ahead to see where the road is leading. It prevents that common feeling of being lost in just a sequence of isolated, unrelated worksheets.
Right, avoids the what's the point of this feeling. And frame number 2 is where the synthesis happens, the invention page. The sources sometimes call this the multidimensional view. This sounds crucial for encouraging that dialectic stage of learning.
Oh, it absolutely is. It's the ultimate synthesis tool. The idea is to pull together related concepts that might have been taught weeks, months, or even years apart in completely different domains. The example the sources give is limits. The invention page might show how the idea of a limit connects concepts taught way back in early arithmetic, maybe lesson 4, then limits on a line, like in lesson 9 dealing with asymptotes perhaps, and then later limits explored in 2-dimensional space.
So it's forcing the student to step back and kind of connect the dots themselves.
Precisely. Its goal is really self-assessment. It poses this big challenge, okay, tell me everything you know about limits. If the student can actually articulate those connections across dimensions, that shows grammar and dialectic mastery, then they're ready for the rhetorical stage, applying the knowledge.
Okay, that makes sense. Moving on, we have the other 2 frames. Frame number 3 is the memoria and arrangement page. You said invention is about synthesis, so what role does this sister page play?
This is the essential grammar tool, really. This is where those 16 fundamental functions we mentioned, the core vocabulary of math, are summarized. It's essentially the student's go-to reference chart. But the key detail the sources emphasize is the arrangement itself. The way the functions are categorized and ordered, that's meant to convey meaning and aid understanding, not just, rote memorization. They're grouped by their fundamental form or behavior, forcing the learner to compare and contrast them visually.
So that structural element is key. They're kind of embedding the dialectic right into the memorization tool itself.
Clever.
And finally, the careful calculations page at the back.
Yeah, this one is pretty straightforward. It's about repetition. It emphasizes calculation practice, often using substitution activities that reinforce those mechanical skills. It's a completely versatile tool. It can be used for daily review, maybe a short quiz, or even a comprehensive test. It just ensures students maintain fluency with the mechanics.
And the most important takeaway about all 4 frames seems to be their flexibility. These are tools, yes, but they're not mandatory activities.
Not at all. The sources specifically state there is no one way to work through the booklets. Families and educators are encouraged to use them as deeply or as lightly as needed for that particular week's lesson.
That focus on flexibility really sets the stage for our next segment, doesn't it? That's right. That flexibility is crucial because, let's face it, conventional curricula can be so rigid. The goal here sounds like communities holding the same weekly topic, say, functions, but allowing every student to tailor the path to their exact needs. But wait, if the curriculum is trying to avoid rigidity, how can focusing intensely on grammar loading via flashcards be the right answer for some students? That sounds, well, highly structured.
It is structured, but only temporarily, and it's very targeted. For a student who's really struggling with the concepts, the immediate need isn't necessarily high-level understanding, it's fluency in the language itself. That's grammar loading. You focus intensely on flashcards, memorizing vocabulary, formulas, facts out of context. It's exactly like learning Latin vocabulary, really. The better you know the grammar, the faster the deeper dialectic and rhetoric work becomes accessible later on. The memorization frees up mental bandwidth, you see.
Okay, so we can adjust the input based on the student's current proficiency. How else can the depth be adjusted? What about the output?
Well, we can scale the required output. For a student needing support, you might use the solutions pages as copywork. We know that the physical act of copying equations and explanations is actually a powerful way to reinforce learning. Or, let's say a student is working on a high-level algebra lesson, but the computation itself is just overwhelming them that week. You can incorporate calculations from a lower domain, maybe computational problems from the fractions level, into their daily practice. They get to master the concept without being totally bogged down by calculation complexity.
That makes a lot of sense. And what about for students who are already confident? The ones operating more at the rhetoric level?
You challenge them with application. You encourage them to engage with the material using those classical common topics, comparison, definition, circumstance. And the highest level of tailoring is really challenging them to teach or explain the concept to someone else. I mean, if you can clearly articulate the distinction between an exponential function and a power function, you've definitely achieved rhetoric mastery.
That distinction between focusing on grammar, comparison, or application, depending on the student's need, makes perfect sense. Okay, here's where the architectural design of the curriculum gets really impressive to me. This intentional alternation of difficulty.
Absolutely. The sources cite this as a deliberate strategy. It's there to prevent burnout and encourage persistence. The curriculum actually schedules restful weeks immediately following challenging ones. For example, Lesson 11, which deals with advanced functions, is cited as a challenging week, right? But Lesson 12 is purposefully restful and familiar, covering basic geometry. Week 18 is another one mentioned as being particularly difficult, likely followed by something more manageable.
Wow, I wish my school math had done that. That built-in rhythm basically tells the student, look, persevere through this dense material because next week is designed to feel comfortable and familiar again.
It's a psychological anchor, really. It respects the fact that true learning takes time and energy, and you just can't maintain peak cognitive intensity for 30 weeks straight. It builds in recovery time. So let's use Lesson 11, that challenging one covering curved lines and functions, just to illustrate the learning approach. The challenge here is definitely the notation and the complexity. For a younger student, the primary goal that week is often just familiarity with the symbols, not necessarily full conceptual mastery right away. You're just getting used to seeing fxx.
Okay, so that means we slow down and look for those foundational patterns. The lesson looks closely at exponential functions, right? Comparing three different cases based on the b of the exponent. What patterns are the students encouraged to find visually just by looking at the graph?
They focus on the behavior of the line, connecting the symbol, which is the base value, to the visual, the direction of the graph. So if the base is between 0 and 1, like 1/2, the graph goes down. This represents decay. If the base equals 1, well, the graph is a boring, stable, horizontal line. That shows no change. And crucially, if the base is greater than 1, the graph goes up. This is growth. That comparison right there is dialectic in action.
So the central message is that every algebraic relationship has a visual twin. That leads to the core big idea that every equation with two variables like x and y, or fx and x, has a corresponding graph or image.
Precisely. And the shift in notation from y to fx is actually part of the grammar lesson itself. While they're often interchangeable, using fx meaning function of x is just clearer for distinguishing between different functions, like an fx versus a gx. More importantly, the sources stress how students can look at the symbols, like seeing that x is being squared, x squared, and predict the graph, knowing y values will always be positive before plotting a single point. You're learning to read the language and predict the image.
Okay, and here's what seems like the most powerful aha moment the sources highlight for pattern recognition. This feels like a true shortcut across all 16 functions. We often see the general equation written with a times x minus h to the n plus kh and k look like just more letters to memorize, but their power is universal.
This is the genius of the architecture, I think. H and K operate like a universal GPS system for every single function in mathematics. H dictates the horizontal shift left or right, and K dictates the vertical shift up or down. The insight is that this rule never changes. It doesn't matter if you are dealing with a parabolic function, a cubic function, a logarithmic function, or way down the line, a trigonometric function. H and K always tell you where the parent function, that basic version anchored at the origin, has moved.
So the real genius lies in the consistency of that pattern. That means once a student masters the simple parent function of, say, x squared, and they understand h and k, they suddenly know how to graph an infinite number of related parabolas. And they know the fundamental structure of tons of other functions, too.
It simplifies every complex graph into something known that has simply been shifted. It's the ultimate antidote to that information overload we talked about. If you understand H and K, you can effectively skip hundreds of pages of rules specific to individual function types. It's incredibly efficient.
Yeah, that's powerful. The lesson also introduces the necessary, maybe sophisticated language for describing these curves, things like maximum and minimum points, or the concept of end behavior, which describes what the graph does as x gets really large or really small. We also see terms like concave up and concave down.
Yes, and while that language can sound dense at first, it's just vocabulary. Concave up just means the curve looks like a cup holding water. Concave down means it looks like an umbrella spilling water. It's the descriptive language needed for rhetoric, for talking precisely about these shapes. And repeated exposure through the frames and the lessons just makes it familiar over time.
That dense language brings us right to Lesson 12, the restful week, covering polygons. It provides a familiar physical anchor after that more theoretical deep dive into functions.
Exactly. This is geometry, so we revisit familiar grammar. The definition of a polygon: closed shape, straight sides, and we revisit that essential dialectic comparison. The difference between perimeter, which uses simple addition of sides, versus area, which requires multiplication. Basic stuff, but reinforces core operations.
Okay, here's the really fascinating part, connecting geometry back to a tangible physical experience to embed the grammar. The curriculum actually suggests a hands-on experiment to discover the famous triangle rule.
That's right. Instead of just stating the rule like A plus B must be greater than C, the lesson directs students to gather common household items of different lengths. A ruler, a pencil, a knife, a spoon, maybe a fork. They are instructed to physically try to build a closed triangle using 3 of them.
And what do they inevitably discover through just trying to do that?
They discover, through physical trial and error, that the 2 shorter sides must add up to be longer than the 3rd side for the shape to actually close. If they choose, say, a pencil short, a fork medium, and a ruler long, and the pencil plus the fork are shorter than the ruler, they physically cannot connect the ends to make a triangle. The sources really emphasize that this physical, kinesthetic experience is incredibly powerful for memory. It helps later recall of this geometric truth much more than just memorizing a formula.
That experience creates an anchor. It stops the rule from being just some abstract equation. It makes it feel like an inherent property of reality, something you've actually tested.
And it solidifies the overall value of constantly looking for patterns, even with simple shapes. For instance, comparing the square to other quadrilaterals, they observe that the square is the only regular quadrilateral among the common examples shown. It's just constant comparison, constant dialectic, even in a restful week. #outro.
So what does this all mean for the learner, for you listening? The sources suggest that by slowing down, focusing on the grammar, those 16 functions, and intentionally reading the math aloud, much like you might read a complex philosophical text, and using flexible contextual tools like the frames, these overwhelming math concepts actually become digestible, familiar.
Yeah, the core benefit for you, the learner, is achieving rest and confidence. When you recognize that universal structure, that H and K shift every function the same way, or that the concept of limits is layered across different dimensions of math, you realize you aren't facing thousands of random rules. You're facing maybe 16 foundational ideas that are simply arranged differently each week. That consistency provides real cognitive rest, even when the notation looks scary at first.
So here's the final thought for you to mull over. If mathematical language is really just vocabulary that needs repeated exposure to become familiar, what intimidating text, be it complex legal documents, a dense treatise on physics, maybe even the Constitution, or a historical math text, could you approach today simply by slowing down, focusing on the key vocabulary, and maybe even just reading it aloud? That's your next deep dive.